Today I'm going to read Chapter 2 of Chemistry, Getting a Big Reaction. Modest and unassuming, this bunch of founding fathers is rarely glimpsed. Yet these backroom movers and shakers are the building blocks of matter itself and the stuff from which the whole universe is made. Their properties govern the stately flow of energy as bonds uncouple and relink, as atoms and molecules move from one compound to another. It is their behind-the-scenes activities that underpin chemical reactions and give the lab rats all the bubble and explosion they need. You have to keep your eye on this bunch. They're nuts. So you can see the bunch there. We will be talking about atoms, isotopes, ions, molecules, giant molecules, polymers, metallic bonding, nanoparticles, Avogadro's number, the mole, and smart materials. The atom. Smaller than a pinprick, but larger than life. Atomic particle that has no overall electric charge. The periodic table is an arrangement in atomic number order. I am the stuff the universe is made of. I am every chemical compound. In fact, I am everything that you can see, touch, and breathe. I am like a planetary system in miniature. My central nucleus is made up of extremely tightly packed positive charged protons and neutral neutrons, orbiting in energy levels called shells around this heavy positive core are my zippy negatively charged electrons. The shells wrap around the nucleus like the layers of an onion and are filled from the bottom up, the lowest energy to the highest energy. The first shell holds only 2 electrons, the second holds 8, and the third holds 18. I hold on to my protons and neutrons for dear life. The number of protons determines what type of element I am, but it's the electrons in my outer shell that I use for chemistry, by pairing and sharing with other atoms or by moving them across to other atoms to create ions. 500,000 atoms could line up across a single human hair. I love the human hair reference because hairs are about 80 micrometers and atoms are about 1 angstrom or 0.1 nanometers. Okay, the number of electrons equals the number of protons in an atom. The atomic number is equal to the number of protons, but the mass number is equal to the number of protons plus the number of neutrons. So there you go. There is a picture of a little anthropomorphic atom. Very cute. Looks like a helium. Isotopes. Atoms with equal atomic numbers, that is, equal number of protons, but different mass numbers, that is, different numbers of neutrons. Goblins with varying numbers of neutrons in their atomic nucleus. Isotopes that decay are called radioisotopes. Like the ghastly creations of some crazed scientist in a low-budget sci-fi movie, we're atoms' monstrous brothers. With the same number of protons as our atomic siblings, we have the same chemistry and undergo the same reactions. However, we have a different number of neutrons in our outer nuclei. Sometimes more, sometimes less. This unhealthy number of neutrons gives us a nasty streak. A normal atom tends to be stable, while our unbalanced nuclei can decay. That is, they can lose or gain protons and neutrons, leaving new elements. Medicine makes good use of our radioactive decay, but we are most famous for our destructive power. Radon isotopes in granite give people cancer, while uranium-235 and plutonium-239 are the active ingredients in nuclear weapons. Carbon-12 is a normal stable carbon, which has 6 protons and 6 neutrons. But carbon-14, it's carbon, so it still has 6 protons, but it has 8 neutrons. So it has a higher mass number and it's slightly more dense. And it decays. That is, it changes into other elements. It changes the number of neutrons and protons by a process called beta decay, but that is beyond the scope, perhaps, of today. Ions. An atom that has gained or lost one or more of its electrons is an ion. There are strong electrostatic forces that hold these guys together, that makes metals and nonmetals connect in salty crystalline lattice. Let's get this party started. It's all well and good to admire atom steadiness, but you want a bit of spark and pizzazz in your chemistry, don't you? No atom, aside from the elements of group 8, has a full set of electrons in its outer shell. My trick is to transfer electrons to or from the outer shells to fill them up. This creates positively and negatively charged ions, making lots of exciting chemical reactions possible. Opposites indeed attract. I join positive metal and negative nonmetal ions together in a tight embrace with my ionic bonds. The ionic compounds are rock solid with high melting points and boiling points. Brittle crystals that dissolve in polar solvents like water, and conductors of electricity when molten or in solution. Table salt is a well-known ionic compound. It's sodium chloride. Group 1 and 2 metals, that is like sodium, magnesium, they lose 1 or 2 electrons to become ions of +1 or +2 charge. Groups 6 and 7, that is oxygen and fluorine, they would gain the electrons, filling up those last 1 or 2 shells to become -2 like oxygen, or -1 charged ions like a fluoride ion. The melting and boiling points of ionic compounds is high. That is very high even. Molecule. 2 or more atoms held together by a covalent bond. They have a calm character who relies on a spirit of mutual sharing. Nonmetals that are slushy at room temperature. There's nothing flashy about me. I'm a safe pair of hands who is more like a geography teacher in a faded out old suit than a superhero. Quiet and unfussy, I let 2 or more nonmetals combine, making an electrically neutral, stable substance, such as water or nitrogen. Nitrogen gas is diatomic nitrogen. Rather than rob atoms of their electrons, transferring them around willy-nilly, like that shameless ion we just read about, I prefer to allow nonmetal atoms to cooperate in filling their outer shells of electrons. This flexible and strong form of chemical bonding is called covalent bonding and is used by many simple molecules. My covalent compounds have low melting and boiling points because although the bonds between the atoms are strong, the forces of attraction between the molecules are relatively weak. Molecules with high atomic numbers have strong intermolecular bonds. Bonds between atoms are strong, but the intermolecular forces are weak. The smallest molecule is hydrogen, which is 0.0000015 millimeters, or 1.5 angstroms, which is 0.15 nanometers. I don't know why they put it in millimeters. It's a little bit hard for me to relate to. It's incredibly small, though. Okay, so giant molecules. This diamond powerhouse is a girl's best friend. A massive lattice work with a huge number of bonds. A titan who works with carbon or silicon or oxygen. I'm a covalent colossus, a behemoth of bonding. Atoms in my mammoth molecule are linked together by strong covalent bonds, like a towering superstructure of interlinked supports. Because each atom is tightly bonded to its neighbors, I am usually very hard, sometimes brittle, and I have a very high melting point. That's why diamonds are forever. So the hardest giant molecule is a diamond. It has a melting point of very high, like 3,600 degrees Celsius. And there you can see a picture of my giant molecule. Okay, polymer. Chains of small molecules, or of a string of atoms, this Mr. Poly giant molecule. This multi-purpose fellow comes in thousands of useful forms. Man-made polymers are the wonder material of the past century. I'm plastic. I'm possible because millions of simple repeating hydrocarbon molecules, known as monomers, can connect to make a giant chain link molecule. I have many natural occurring varieties, but my man-made types, which are cheap to produce, can be almost anything you want them to be. Pliable or rigid, soft or hard. For a groovy 1970s vibe, just check out polyester. It's like one big long daisy chain. Natural polymers include stuff like cellulose or amber. Man-made polymers are nylon or PVC, which is polyvinyl chloride, or polyethylene, polypropylene, etc., etc. They're created with a reaction called polymerization. So polymers are made by polymerization. That's kind of a self-referential term, isn't it? Anyways, they're used to make plastic bags, bottles, rubber boots, surgical instruments, car panels, etc., etc. Metallic bonding. Behind-the-scenes character that binds metal atoms together. A lattice of positive ions surrounded by a sea of free electrons. A big softy who is the reason why metal is a good conductor of electricity and heat. Inside the dark heart of that hard-cased metalhead metal, you'll find me. One of the 3 important types of chemical bonding. I link together metal atoms just like ionic bonding creates ions, and covalent bonding chemically joins molecules. The properties of metals are based on the way I bind their atoms. Internally, the metals are arranged into a lattice of positive ions with seas of free electrons washing around in between them. The electrostatic force of attraction between the ions and electrons holds the whole thing together, but the electrons are also free to move around through the giant structure. Because of this, metals are great conductors of heat and electricity. The flexible internal arrangement also allows metals to be shaped easily and hold an edge well. I'm one sharp cookie. Metals are shiny because light hits the sea of electrons and is reflected. That is, another photon goes back away from those sea of electrons because of the movement of the free electrons in the metal. Interparticle forces are very strong. Free electrons are delocalized electrons, so they don't really care where they are. They're kind of spread all around. And the melting points and the boiling points are usually high in metallic bonding. So you can see there's a picture of the positive ions in the metal and then the free electrons floating all around in little metallic bonding's shield. Nanoparticles. Tiny particles that have very unusual properties. No blockheads, they behave very different from large lumps of stuff. They get added to materials to lend them superpowers. We live in the realm of the itty-bitty. Forget the flea. Things in our world are just a few atoms wide. We are an array of dazzling shapes, cuboids, rods, spheres, and bananas, all that are 10,000 times thinner than a cat's whisker. With each of our minuscule particles comes unexpected talents. Let's take a lump of silver. It has the natural properties to kill bacteria and fungi, where a sprinkling of nanosilver acts like a ruthless killer of germs and superbugs. Why? Because it has much more surface area compared to its volume, which makes the atoms on its surface much more reactive and powerful. Sometimes it is just our teensy size that makes us special. Zinc oxide nano, amazing absorbers of UV light, are added to sunscreen because they're invisible to the naked eye. A nanometer is 1/1000th of a meter, and the size of a nanoparticle is 1 to 10 nanometers, And the study of nanotechnology and nanoparticles is called nanoscience or nanotechnology. It means understanding things at the size of 1 nanometer, which is pretty much my job. Avogadro's number. Okay, a real bigwig whose real name is the Avogadro's constant, a number that tells you how many molecules are in a mole of gas. It's just a definition thing. It's a way of counting up atoms to keep track of how many there are so that you can know what their volume or mass will be. You can count on me, I'm a constant. My special number, like a dozen eggs, tells you exactly how many atoms you will find in a specific quantity of any gas at a certain pressure or temperature. This number is 6.022 times 10 to the 23. So it's an incredibly large number, which just reminds you just how small, and we keep talking about this, atoms are. They're tiny. It's a very big number. And if you had that many cans of soda, they would cover the planet in a blanket 200 miles thick. So, Avogadro's constant is 6.022141179 plus or minus 30 times 10 to the 23 atoms per mole. It was named after Amadeo Avogadro, and it's just a definition. The mole. This refined fellow isn't a mole who lives in a hole. It's a unit of measurement. It's a way of counting. The high-minded chemical counting. 1 mole has 6.02 times 10 to the 23 particles, like we just said. Atoms are very small and devilishly difficult to count. So I help with a useful piece of backward thinking. 1 mole serving of any element or compound always contains the same number of atoms or molecules as given by Avogadro's number. The weight of each mole is equal to the atomic mass of the element, measured in grams. That's the definition of a gram mole. 1 mole of oxygen weighs 32 grams because it's diatomic, and the atomic weight of oxygen is 16. 1 mole of carbon, how much does that weigh? Anyone know the atomic mass of carbon? It's about 12. Okay. Smart materials. Futuristic new materials with amazing properties. Sensitive souls who respond to heat, electricity, pH, and stress. Sharp and intelligent and out to change the world. We're real smart cookies. We point to a wild time ahead when materials will respond to changes in the external environment. But don't think we're only sci-fi make-believe. One member of our gang includes the super voltage sensitive electrochromic materials in LCDs, liquid crystal displays, that change the color and transparency of an LCD screen. That's actually how screens work, probably that you're using to watch this video right now. We can give metals and plastics a memory by sprinkling in some nanoparticles. Our technology is also used by some glasses frame. Squash them and our shape memory alloy will bend it back to its original shape without any help from you. We can even learn certain behavior. One day your toilet seat will warm up when you sit on it, and your wallpaper will play music when you enter a room, and your fridge will change its color to suit your mood. Sweet. Smart molecules were first used, according to this book, in the 1980s. And the smart memory plastics are called SMPs. And a common smart memory alloy is nitalol, a titanium nickel alloy. Okay, there's a smart material. So we will leave it there for tonight. And next week we will talk about nasty boys, acids and bases. Should be good. Bye.